Boldly going where no science show has gone before. The Naked Scientists.
For this special Naked Scientists, we'll be looking at both naked astronomy and naked archaeology. I'm Diana O'Carroll.
And I'm Ben Valsler. The sciences of space and human history may seem like strange bedfellows, but every month we look at the latest news and fascinating discoveries in both, and we thought we'd highlight some of them here.
So, coming up, I'll be looking into Bronze Age burial practices, meeting some of our oldest known walking ancestors, and finding out how past human migrations are written in our genes.
And I'll explore the challenges of building extremely large telescopes, find out how Rubik's Cube-sized satellites can help test new technology, and consult a team of experts to answer your questions on dark matter, planets, and spacecraft propulsion.
That's all coming up on today's Naked Scientists.
Bringing the facts to bear. The Naked Scientists.
This is The Naked Scientists with me, Ben Valsler.
And me, Diana O'Carroll. A slightly grisly start to this week as we're looking at Bronze Age cremations. During the period, which spans roughly from 2000 to 700 BC in the UK, there was a fashion for cremating the dead. Joe Appleby, a postdoctoral researcher in the University of Cambridge's Archaeology Department, has been studying these very early cremation burials, plus some which appear even earlier. And the information that can be drawn from them is quite surprising. Listeners of a sensitive nature are warned that this interview does contain some graphic descriptions of what happens during the cremation process.
I'm looking at the changing nature of burial practices from the mid-3rd millennium BC through to the end of the Bronze Age, and trying to figure out the changes in ways that people approached death and burial over that time, in particular looking at the practice of cremation.
And what kind of changes do you see happening?
Well, during the beginning of the early Bronze Age, we see the first introduction of cremation as a burial ritual, and this is at first quite sporadic and only occurs occasionally. It then, as the Bronze Age progresses, becomes the most common form of burial, and then eventually towards the end of the Bronze Age we find that formal burial rites almost disappear from the landscape. We find occasional burials, but the majority of the human remains we find are as isolated deposits within settlements, and in fact we're not very sure what was happening to the majority of dead individuals at all.
And do you have any ideas as to why these changes were occurring?
Well, that's the interesting thing, and one of the things that my research is aiming to investigate, because burial is quite a good way at looking into people's minds in the past. Death is a very stressful sort of a time, and therefore when it comes to funerary behaviour, you don't just do anything. You want to do something that shows your respect for the person that has just died. It has to fit in with your own cultural beliefs. So obviously bringing in a dramatic change, like going from burying the body as an inhumation burial to setting fire to it, is something quite dramatic. And in the past, it's often been interpreted as a change of people, a new kind of people coming in, but actually it's quite difficult to interpret the beginning of cremation straightforwardly in this way because we don't have the evidence that that was occurring. So instead we see this as a change of belief. And part of what I'm trying to do is to tease out precisely what's actually occurring within the cremation rituals. So not just saying were they burning the body or were they not burning the body, but looking at what they were doing when they weren't burning the body and what they were actually doing when they were burning the body, and trying to figure out what the similarities and differences were that were occurring.
So you've been working on a Bronze Age site. Can you tell me a bit about that site?
Yes, I've been working on a site from Erith out in the Fens, which was actually excavated by the Cambridge Archaeological Unit, and I've been collaborating with Natasha Dodwell of the Archaeological Unit on this. The site originally consisted of a ring ditch with a central inhumation. This was constructed in the early Bronze Age. And then this later became the focus for a Middle Bronze Age cremation cemetery where over 30 individuals were buried.
And we've got a couple of examples here. So let's look at this big tray. It's full of quite a large collection of small bits of, they look quite burned, bone. What actually do we have here?
Okay, well, we do indeed have a large tray full of quite small burned bits of bone. But what this can do is it can actually tell us a little bit about what was going on. So despite the fact that these bones to the untrained eye look as though they could be pretty much anything, they are actually identifiable if you know what you're talking about. So For example, I can pick out a piece here which is about 5 centimetres long and quite warped and doesn't look like much of anything, but I can tell you that's probably part of a human tibia, so that's one of the lower leg bones. As well as being able to identify that, I can tell you that the bones in this particular tray are of adult size, so we're dealing with an adult individual, and in fact this individual has been identified as male. But there are also some infant bones buried in with this individual. I don't think in this particular tray, because the bones are sorted by size and these are much smaller, obviously. So we can determine the age and the sex of individuals and whether we're dealing with one person in a burial or whether we're dealing with more than one person, and that actually occurs relatively frequently. In addition to that, I can tell you something about the temperature at which the bones were burnt. So the majority of the bones in this tray are actually white. And you might think that the skeleton is naturally white, but in fact it's, generally speaking, more of a creamy yellow colour when we excavate human skeletons. And this white colour tells me that the bones have been heated to more than 600 degrees. So that's a high temperature, very efficient cremation practice that we're seeing. In addition, the bones are quite warped and they're quite fractured. And that's to do with the effects that the heat has on the organic component of the bone. So bone is a matrix made out of organic proteins and an inorganic material that gives it a great strength. And obviously when you cremate bone, then you lose the organic component, but you retain the inorganic component. When the organic component is present, the burning up of that causes the bone to warp and change shape. So from the fact that this bone is warped, I can tell that this individual was burnt when the bone was still fresh, as opposed to them having dug up some old bones from somewhere and then set fire to them.
Do you see the same sort of things happening across all the burials?
This kind of practice, I would say, was typical for a burial of this period. In the Middle Bronze Age, cremation was typically quite efficient. It was typically involving individuals soon after death. Generally speaking, it was only one person being burnt at a time. In the earlier period, it was more variable, and in the later period, it was quite weird, and we're not totally sure what was happening.
Okay, we've got another tray here of a collection of, it looks like 5 bags of all sorts of different bits of bone. So what's going on here? What's different with this one?
Well, these are just some pieces that I picked out to illustrate some of the things that we can see when we look at bone. So here I've got a bag with a piece of tooth in it, and this is, in fact, a human molar. And when we look at it, we can see that we've got some sticky out bits at the bottom, which are actually the roots, and there's not much left of the crown of the tooth. And this is because as the enamel heats up, it actually explodes. So what we tend to find when we find teeth is just the lower proportion. When we do find enamel, it's often because it's unerupted teeth from children which were still sitting inside the jaw, and so the presence of the bone of the jaw has actually protected the enamel. And so that can be a clue as to the age of the individual that we're dealing with. I also have a bag with a rather large bone in it, which comes from the ankle of the individual. And when we look at this bone, we can see that the coloration on it is quite variable. So it goes from everything to a sort of a dusty brown colour, through a bluish grey, through to white in certain parts of it. And this is an indication that it's been subjected to varying degrees of heat. So it's not totally burnt out. There was still organic material remaining in this bone at the end of the cremation process.
Do you find that happens a lot to extremities, like feet?
Well, it's quite interesting because it happens according to the amount of tissue that is protecting the bone. And obviously, right within the ankle joint, which is where this bone has come from, then there's quite a lot surrounding it of quite dense material that's preventing it. But actually we find that some parts of the body which we wouldn't expect to survive in that fashion do quite well, and that's because of the way that the body reacts to extreme heat. So when you cremate a body, the heat actually causes certain muscle groups to contract, and that puts the body into a position that is known as the pugilistic posture, where the arms are drawn up, the hands contract into fists, the legs go into what looks almost like a frog-like sort of a posture. And this means, for example, that the very ends of your finger bones, which you might expect to be burnt very early in the process because there's not much flesh around them, actually when they're drawn into the fist, then they're very much protected, and so they're one of the last bones that burns. So here I've actually got the very end finger bone from somebody's hand that survived the burning process quite well.
Oh, it's absolutely tiny. It is incredible that something so small has survived.
Yes, and of course sometimes what happens is that these smaller bones actually fall off and fall through the pyre, and that can be another reason why they get protected and don't get burnt up so much.
And these bones are all several thousand years old. So how is it that they can survive even though they've been burned quite heavily and then presumably interred in the earth?
Well, we have a slightly strange idea about what cremated bone ought to look like, because when our beloved relatives sadly die and we take them down to the local crematorium, what we get back is an urn full of tiny, unrecognisable ashes. That's not actually what you get at the end of the cremation process. What you get at the end of the cremation process is essentially a skeleton where some of the bones are a bit fragmented, but they come in very large pieces. And because they've been burnt, they're brittle, but they're still very recognisable. And in modern crematoria, they actually have a special machine that breaks up the bones into a powder so that you cannot recognise any specific part of your relative if you decide to scatter the ashes, because that would obviously be upsetting for you. So these individuals in prehistory would have gone into the ground in really very large pieces. And whilst they don't survive complete, they survive reasonably well. And in fact, cremated bone actually, in many conditions, survives better than uncremated bone.
So if you want someone to find you in a few thousand years and you're currently in a temperate climate, perhaps the best option is to get cremated the Bronze Age way. That was Joe Appleby from the Department of Archaeology at the University of Cambridge.
So cremation actually helps to preserve bone, and I would have thought it would be quite the opposite. But moving on to the first bit of astronomy in today's show, Douglas Adams found a very good way to describe how big space is. He said, "Space is big. You won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down the road to the chemists, but that's just peanuts to space. In order to see into the far corners of space, to make the invisible visible, we need bigger, better, stronger telescopes. But building these presents a number of engineering challenges, as I found out from Professor Colin Cunningham from the UK Astronomy Technology Centre."
Well, we've been building telescopes for 400 years, and gradually they've got bigger and bigger, and it's usually been driven by what technology is available. So Galileo started off by using sort of spectacle lenses and a cardboard tube, and we've now gone to building sort of 8 to 10 metre mirrors, which have given us a fantastic new view of the universe. But what we've found now is, because we've got the technology that was developed to allow segmented mirrors, so we take lots of hexagonal segments and join them together to make a bigger mirror, we're not stuck with the sort of 8 metre size. We can go bigger and bigger. In fact, we're only stuck by the amount of money we've got, basically. So we can build a big telescope, and at one time we were looking at building a 100 metre diameter one, but now we've been more sensible. We're talking about building a 42 metre telescope, which is very big. And the big thing it does, it's two things. It gives you much more sensitivity, so it collects so much more light than all the other research telescopes in the world put together. And if you put that together with the fantastic spatial resolution, in other words, the detail that you can see with this telescope, you can really do very, very faint objects like the early universe, like early galaxies, understand them, actually do astrophysics and find out how they're rotating and merging and all that sort of thing. And you can also look at nearby things, or relatively nearby things, like planets around stars. Because you can do that, you can actually understand much more about them. You can look at their orbits. Potentially, you can even look at their colours. And we might even find some that are similar to the Earth. So that's why we want a bigger telescope to do all these things that we can't do now.
So what are the engineering challenges with building something this big?
Well, it's very much bigger than we've done before, as I've just said. The telescope itself is made up of 984 individual mirror segments, each of which is 1.4 metres across. So each of them is quite big. And you've got to keep them together in a nice, perfect shape as the telescope moves around the sky and as gravity varies because of that. And you've got to keep them aligned to something like 10 nanometers, which is very, very challenging. So you've got to have lots of instrumentation, lots of control systems to keep all that working properly. And that's got to work very reliably all through the night and year after year. And on top of that, we've also got to deal with the atmosphere. In some ways, our life is quite difficult with ground-based telescopes. We've not only got to deal with gravity varying, but we've also got to deal with the atmosphere varying. Because if you build a space telescope, you don't have to deal with either of those things. But on the other hand, you do have to launch the thing, which is expensive and time-consuming. So what we think we can do on the ground now is by using something called adaptive optics. We can get over the limitations of the atmosphere. The atmosphere moves around and blurs the images. But we can measure the amount of blurring by looking at a natural star and measuring the wavefront from that star. Or we can put an artificial star about 90 kilometres up in the sky by using a laser, and we can measure the wavefront from that. If it's distorted, we measure that distortion, and then we apply the opposite of that then we've got effectively a perfect image. And this means we can get fantastic image quality, which you couldn't do in space because you couldn't ever launch a big enough telescope.
We've had segmented mirrors, these hexagonal individual mirrors, for a while. Can we just scale up the technology used there, or does the sheer size of this present a whole unique set of challenges?
It's pretty much the same technology. The big problem is just the scale of it, really. The current biggest telescope in the world with segmented mirrors are the Keck and the GTC in Canary Islands. They've got 36 segments. Making one of those segments at the moment takes about 6 months. So it's actually the manufacturing process. If you multiply 6 months by 984, you realise we're not going to be building this telescope in anybody's lifetime. So we've got to make one of these mirrors, basically one a day. So we need new technology to do that. And we've got new technology actually in the UK. There's a consortium of organisations working in North Wales at the Optic Technium that are making prototypes for this telescope now. And they've got some new technology that allows us to do it much quicker so that the telescope is possible.
Do we also have to find new materials to get over some of these challenges? I assume that these mirrors aren't the sorts of mirrors I have at home, a sheet of glass with a very thin film of aluminium on the back.
Well, strangely enough, they are, pretty much. It's better glass than you've got on your mirror in your bathroom. It's low expansion glass. It's quite tricky to manufacture, but it's the same thing that people have been using for about 150 years, really. It's a glass ceramic with a coating of generally silver these days as opposed to aluminium. And we've looked at new technologies, new materials like silicon carbide compounds and composites and even carbon fibre composites. And they do give you some advantages. They're usually a good deal lighter, which means the rest of the structure can become a lot lighter as well. But the general feeling is that they're not really there yet. And the conventional glass ceramic coated with aluminium or silver held on a steel structure is actually the best thing to do.
Can we apply any of the lessons that we've learnt with this to more mundane things?
We certainly can, and we already are doing. The adaptive optics technologies that we use to correct the images from the sky can also be used to correct images used for looking into your eye, so looking the other way. So you can use adaptive optics to actually improve the quality of an image of the retina and look at individual rods and cones, look at the blood vessels and actually measure blood flow in those blood vessels. So that's the only way you can do that, of course, without cutting somebody open. That could be very important in terms of diagnosis of diseases like diabetic retinopathy. If you go to the opposite extreme, the technology we're learning in order to make mirrors at a reasonable cost and a reasonable speed, we can use that for laser fusion in the future. Already people are building laser fusion systems in order to get green energy, basically reproducing what happens on the sun. There's no radioactivity, there's no carbon emission, and you get almost an infinite supply of energy. If this works, this could save the planet. And we can do this using the technology we're developing for astronomy. So that's pretty good, if you ask me.
Colin Cunningham explaining how technology developed for stargazing may help to see inside your eyes or provide ways to generate clean electricity, as well, of course, as seeing further into space.
So do astronomers get telescope envy?
Well, I think that many of them would claim that it's not how big it is, but it's where you put it that counts. For example, there are only a few sites on Earth good enough to detect much in the way of infrared radiation from space. Our atmosphere absorbs too much. So you either have to get above much of the atmosphere, like in the Atacama Desert in Chile, or even out into orbit. So where you put it really is more important than size.
Indeed.
Lifting the lab coat on the world's best science. The Naked Scientists.
This is The Naked Scientists with me, Diana O'Carroll.
And me, Ben Valsler. Still to come, we find out how tiny cube-shaped satellites can help to test new technology, and my expert panel will tackle your questions.
But first, the 2-million-year-old Australopithecus sediba has been described. This transitional species of early human could link the two-legged Australopithecines, of which the famous Lucy was a member, to the early Homo genus. Sediba had a small brain, but probably walked a bit less like John Wayne than all the others. Professor Lee Berger from the University of the Witwatersrand in South Africa described the discovery to me.
Well, it actually happened after a organized search for sites. I had started a search back in early 2008 using Google Earth, of all things, to look for new cave sites in the Cradle of Humankind area just outside of Johannesburg. At that time, we knew of about 130 cave sites and about 20 fossil sites. By July of that year, by both using Google Earth and then going out and ground truthing with my dog and I just walking in these very remote areas, I'd found almost 600 new cave sites and over 30 new fossil sites. In the end of July, I'd realized that an area very near to where I'd been working for the last 20 years had a series of cave sites that I didn't know existed. And on the 1st of August, I visited them and found the Malapa site, a site that had never been seen before. It was rich in fossils, but it had hardly been touched by miners. This area had been sort of searched over by lime miners in the late 19th and early 20th century. On August 15th, we went back to the site, myself, my 9-year-old son Matthew, and my postdoc Job Kibbe, and a minute and a half later, my 9-year-old son said, "Dad, I found a fossil." And what he'd found was the collarbone or clavicle of an early hominid, and that started the whole thing. And since then, we've been in this remarkable period of discovery. We've discovered arguably the two most complete early hominids ever discovered, as well as others in what seems to be one of the richest paleoanthropological localities in the world.
So what did you do once you found these pieces? Did you take them back to the lab and analyse them immediately? Did they immediately seem different to you?
Well, that's an interesting question. Under South African law, I had to get a permit, but I called the South African Heritage Permit Resource Agency at that time, literally from the site, and got permission to take the first block out. And we began preparing it here. These fossils, if you imagine, are encased in very dense concrete-like substance. And it was very soon that we realized we had a remarkable fossil and that we had what appeared to be an associated skeleton. It was in partial articulation. And I think even early on, I realized that it wasn't at least typical of what we usually find here in South Africa. That is one of the two species, either Australopithecus africanus, that's like the Tong child or Mrs. Ples, or one of the robust Australopithecines, Paranthropus robustus, which have those big sagittal crests across the top of the head. It clearly appeared to be different than that. It would take us a while before we realized it wasn't something like Homo habilis or Homo erectus, but an entirely new species.
And how long did it take to come up with that conclusion to compare all of the species?
Well, that first discovery was a little over 18 months ago, and once we had the skull, and I discovered the skull in March of 2009, we had enough at that point, as we had two skeletons emerging from the rock, that we could compare it with everything that had been compared. And I think the turning point was when my team and I were in the Kenyan National Museum. We just finished looking at all the Homo habilis material, all the material that had been attributed to some of these later Australopithecines, and we realized that what we were looking at was just not found in the range of anything that had been discovered. And we also began to see how unusual it was in its patterning to other early hominids.
So tell me, why is this important? Where does it fit in the grand scheme of things?
Well, firstly, these are probably the rarest sought-after objects on Earth, and to have found literally hundreds of remains of them representing a relatively small number of individuals, well, that really gives us an unprecedented look into any period in human evolution. But, of course, this occurs at a critical point in human evolution, right around 2 million years. In fact, these are dated to between 1.78 and 1.95 million, in fact, closer to 1.95 million years. And that has been a great missing area in the fossil record. Literally, there are only a few dozen fossils, most of them very, very fragmentary from that time period, but it's a critical time period. It's the period between where we have things like Lucy or Littlefoot or Mrs. Ples, these Australopithecines with their relatively long arms and short legs and not moving the way we do, really almost apes that walk on two legs. And then the emergence of what we call Homo erectus, that is something that is clearly very close to a direct ancestor, if not a direct ancestor of ours. And it carries our body plan, a relatively large brain, small dentition, and an advanced face. Well, Sediba falls right in the middle there, and it interestingly carries combinations of both ends of that spectrum. It has these long orangutan-like arms, short, powerful hands, however, and long legs and a very advanced pelvis. In fact, a pelvis very similar to a Homo sapiens or Homo erectus's. Its face is very advanced, its dentition is small, but also has a very small brain, like an Australopithecine. So it's a mix of characters that appear to be both descendant from those earlier hominids and unique and derived to things like Homo erectus.
The thing that struck me was that about, I think it was 9 years ago, another fossil turned up in Georgia, which was supposed to be sort of similarly intermediate. So how do you think these two relate to each other, if at all? How can you even compare them?
Well, Dmanisi is an intriguing question and has been. Some people have said it's an early Homo erectus. Some people have said it's an absolutely unique species. And I think that that's exactly where we should be comparing Australopithecus sediba next, because anyone who looks at them can see a lot of similarities in the face to Dmanisi. Dmanisi does have a larger brain than ours. It does seem to be derived a little more towards Homo erectus, or at least on its own pathway in that direction. But I think sediba might make a very good candidate ancestor, because the big question was, where did Dmanisi come from? It didn't look like a descendant necessarily of Homo habilis or Homo rudolfensis or some of these other things.
And it's 7,000 miles away as well.
Well, but one of the big issues had always been that one of the problems that people had with Dmanisi, and even later things like Flores, is you didn't have an ancestor that appeared to be a facultative biped, something that had come down onto the ground. The one thing with sediba's long legs and advanced pelvis, it's clear it's a very good walker. And it's the kind of thing that could be the type of hominid that expands throughout Africa and potentially would give rise to hominids that could leave Africa.
And so do you think there's anything else that might be in this area where you found sediba? Do you think there's more possibility of similar finds?
Well, I can answer that's not even a question. In fact, we have at least 2 additional skeletons coming out, and we haven't dug yet. The site is remarkably rich. It's a moment in time. It's an extraordinary taphonomic event, and it continues to give us a really remarkable record of this species.
It seems hard to imagine so many different species of early humans with vastly different brain sizes, different teeth, and even different walking styles, all living on the same planet at once. That was Lee Berger of the University of the Witwatersrand, where he's reader in Human Evolution.
I had the good fortune to meet Lee Berger back in 2007, visiting him in his office in South Africa. He's got the most amazing collection of fossils telling the story of our evolution. Once again, changing the subject and bringing us right up to date, the UK Space Agency have recently announced a pilot programme inviting companies and academics to devise innovative ideas for payloads to be launched on a tiny cube-shaped satellite called a CubeSat. To find out more, I spoke to Dr. Chris Castelli, Head of Space Science Projects for the UK Space Agency.
A CubeSat is, as the name implies, it's a very small satellite. The basic CubeSat is cube-shaped, so it has dimensions 10 by 10 by 10 centimetres, and it's a fully functional satellite. The sort of CubeSats you can buy are made out of standardized parts. So this is perhaps one of the most important things to understand. The standardization allows lots of suppliers worldwide to make the various components for the satellites, and you can source these and build these into a standard structure, which is the CubeSat. So the basic building block, the 10 by 10 by 10 cube satellite, is called a 1U. You can make bigger CubeSats. You can go to a 2U, and I think probably the largest size is a 3U, and as the name suggests, it's a sort of oblong-shaped satellite, which is 3 units long.
They're really tiny. When reading about these, I was picturing something perhaps the size of a desktop computer or something around that size. But these are really very small, aren't they?
They are extremely small. You know, a basic 1-unit CubeSat could only weigh just a few kilograms. And you know, a lot of people have said, well, what can you do with something so small? And I think this is where innovation comes into the equation, if you like. If you look at the power of the computing power that is available in your average mobile phone these days, it gives you an idea of the sort of sophistication that you can pack into a small unit now. What is happening worldwide is people are realizing that with very small satellites and advances that are made in microelectronics, putting those together forces people to think about clever ways of doing things where you're limited in terms of mass and power and volume that you have. But nevertheless, you can actually do some exciting sort of things with them. So what we envisage is using a CubeSat as a vehicle, a platform for rapidly testing new technologies in space, for example, where you wouldn't have to go through the more classical route, which takes a very long time of ground-based qualification and testing and more testing before you get to really prove a technology is ready to go on a very expensive multi-million-dollar satellite. You can use a CubeSat as a way of getting an in-orbit demonstration very quickly, very cheaply, and very effectively.
What sorts of technology can you demonstrate with a CubeSat?
If we take the area of space science, for example, future missions that are going to the planets, to Jupiter, for example, or other planets, want to use more sophisticated plasma and magnetospheric instrumentation. They're very sophisticated. They use new technologies, and a CubeSat, even though it's got small dimensions, could be used to test a new generation, for example, of plasma sensor and get some in-orbit verification of how it survives the extremes of space environment. So just putting a new technology into orbit would be one way of using a CubeSat platform. It gets it into orbit in the environment of space, in the radiation, the cold, and the harshness of space, the vacuum of space, and you can get some real in-orbit understanding of how it's performed. The other application of CubeSats is that you can fly many of these. So what people are thinking about doing is flying hundreds, certainly tens of CubeSats into sort of constellation of small satellites going around the Earth. And you can actually, with the advances that are made in imaging sensors, you can get very powerful, sensitive imaging sensors with optics into, say, a 3U CubeSat. And you could actually, with a constellation of these satellites whizzing around the Earth, you can pretty much get global coverage of any point on the Earth within 20 minutes in a very cheap and cost-effective way, which you can't do with any other system. So people are talking about launching, maybe 60 or 70 of these things in orbits that swing around the poles of the Earth. And with multiple CubeSats as a constellation, you can get live images, almost live images every, say, 15 to 20 minutes of anywhere on the globe.
How does launching a CubeSat or a constellation of CubeSats compare with launching a more traditional, larger payload?
Again, it goes back to this idea of standardization. I mean, one way I look at it is, if you remember the PCs, as soon as PCs developed in a way that you could slot cards from various suppliers, so you could get a disk drive from different manufacturers, you could get motherboards, memory cards, you could assemble them all together from standardization. The cost really came down. So obviously the cost through standardization is a key driver. The fact that they're of this known mechanical interface means that low-cost launchers provided by, say, the Indian PSLV rocket, they actually have standard attachments which are designed specifically for CubeSats to go on. So you have a big, say, for example, science or telecommunications satellite that is being launched, and around it are attachments on the launcher interface for CubeSats to go up at the same time. So essentially, the CubeSat is being piggybacked on the main payload, which is paying for the launcher. What you have to pay for, of course, is the necessary licensing and certification to make sure that these things are safe, are worthy, or have a mechanical integrity to go on to the launcher, and they don't sort of fall apart during launch and damage the main spacecraft, which may cost hundreds of millions of dollars.
The UK Space Agency is still really in its infancy.
Yes.
Why are CubeSats a priority for them?
We're looking at this longer term. What we hope to have is a longer term program, a rolling program of CubeSat developments built on the experience of this pilot program. So the pilot program really is just a really cheap way of getting something off the ground, so to speak. What we want to do is have a long-term program of maybe 1 or 2 CubeSats every year to 18 months. Then, therefore, have a rolling call of ideas. We could even have, for example, specific CubeSats which are just targeted at education, at schools, colleges and universities, where students and teachers get together with help maybe from industry and from the CubeSat providers to put little experiments on board. So they act as a vehicle for inspiring and also training young engineers of the future. We want to sort of have a rolling program which then leverages opportunities for the UK in the future.
That was Chris Castelli from the UK Space Agency explaining how CubeSats, devices barely bigger than a Rubik's Cube, can help us to test out new technology in orbit.
Thanks, Ben. I've got a question now. Storm Steve on the Naked Scientists forum asked a question about CubeSats. He said, "My question is about space junk and satellite tracking. There is so much junk currently in orbit that act as projectiles, and the junk can destroy functioning satellites. Won't these tiny CubeSats greatly increase this problem?"
Well, he's right. Earth's orbit is becoming very crowded, but it's a great question. I asked Chris Castelli, who said that CubeSats will only be in low Earth orbits, only 90 to 100 kilometres above the ground, and as there's still an atmosphere up there, that will exert a drag on the CubeSats, and they will quite naturally drop out of orbit and harmlessly burn up in the atmosphere, so existing satellites should be safe.
Laying the facts bare. I say. The Naked Scientists.
This is The Naked Scientists with me, Ben Valsler.
And me, Diana O'Carroll. This week we're looking at the worlds of archaeology and astronomy.
Now, if you're interested in stargazing, you should try out the Open University's Virtual Planisphere. This online interactive tool allows you to track the night sky throughout the year and learn about the stars, constellations, galaxies and everything else that you can see. You can find that by visiting thenakedscientists.com and following the links to the Open University from our homepage.
Well, let's return back to Earth and look at the early moments of a populated Australia. It's not only archaeology that can tell us something about those first settlers. DNA evidence has come up with some fascinating insights into the history of human migrations made thousands of years ago. Thomas Kivisild from the Leverhulme Centre for Human Evolutionary Studies at Cambridge University has been working specifically on the genetics of Australian populations.
Generally, the questions are about the relatedness of humans taken from different continents and trying to relate the similarities and genetic distances observed in DNA with the non-genetic evidence from the archaeology and anthropology.
So we can look at Y chromosomes, which are handed down the male line, and mitochondrial DNA, which is handed down the female line. But once you've got this data from your samples, how do you go about processing it? What are the methods that you use?
There are two types of methods that can be used. One is phylogenetic methods, which is basically building up a tree from the DNA data. And secondly, one can use statistical methods, which basically the DNA dataset is converted into a summary statistic, and then these summary statistics for different populations are compared.
And tell me what you found once you had all this data. I mean, where does Australia fit into the story of human migration?
Firstly, I would have to note that there are a number of different hypotheses that would explain the origin of Australian Aborigines today. Based on archaeological and skeletal evidence, some authors have suggested that there is a possible continuity of the archaic hominin species in Australia because some of the skeletal sites show the presence of archaic features, and secondly, some authors have argued that the Australian Aborigines originated through a rather recent migration from the Indian subcontinent. And while using mtDNA and Y chromosome data, we tried to assess which of these theories would fit with the data. Our results give the high support to the theory which puts the origins of Australian and New Guinean populations, as well as European and the East Asian populations, to the out of Africa migration, which occurred approximately 60,000 years ago.
And that date matches up with the data that you're getting from your DNA evidence?
Most approximately. So the DNA-based tools are never as accurate as the archaeological dates are, and so they also depend on the sample sizes, which are not, unfortunately, as good as we would wish them to be.
So tell me a little bit more about the India theory, the idea that modern Australian Aborigines are more closely related to people in India or southern India. Where did this idea originate and why?
I think the idea is traced back officially to Thomas Huxley, but probably more generally to the age of colonizations, and then when people were looking at the physical similarities that were quite striking between the Australian and the Indian populations, and similarly, for example, the Andamanese populations are physically quite similar to the African populations. Nevertheless, they are genetically more similar to non-African than African populations.
So the out of Africa model still holds. But do you have any evidence for the route that they took to get to Australia?
This is all quite speculative because from the DNA evidence we cannot really tell, but what is still currently one of the consensus views is that the route was the coastal rather than inland, and people talk about two potential hypothetical routes out of Africa, one over the Arabian Peninsula, the so-called southern route, and the other over the Sinai, the northern route. Hopefully the evidence would be found at some point that would definitely be archaeological rather than genetic, because from the study of modern-day populations, such questions cannot be solved in sufficient detail.
You mentioned earlier that it was difficult getting hold of enough samples. Mm-hmm. Why is that? And is there a plan in the future to increase the number of samples and maybe bring this research a little bit further forward?
It depends on the willingness of the people themselves to give the DNA, and unfortunately over the past 100 years there has been a lot of misuse and abuse of not only DNA but also the other biological samples, and therefore some populations of the world, Native Americans and Australians in particular, are not very willing to cooperate with the scientists. Unless this attitude or the conflict between the scientists and the native populations would be solved, then it remained to be difficult to get DNA from them.
Cambridge University's Thomas Kivisild, demonstrating how archaeology and DNA need each other.
It's great to see how biological sciences can be used to support and enhance archaeology, but does this relationship work both ways?
Yeah, so as we discovered with the migrational DNA information that Thomas Kivisild has come up with, sometimes you need to tie that down to dates, and so you can use archaeological evidence. But it works the other way as well, so sometimes you'll have a bit of archaeology and you won't know who made it, who left it there, and this DNA evidence can give you some information as to who was there and how they got there.
Well, thank you very much, Diana. Now, we've assembled an expert panel to take on your space science questions. They are Carolyn Crawford from the Institute of Astronomy at Cambridge University, Dominic Ford from the Cavendish Labs, also at Cambridge, and Andrew Pontzen from the Kavli Institute for Cosmology. Each month they answer your questions for us, and you can find their previous answers at thenakedscientists.com/astronomy. Leo Vila from Miami Beach in Florida got in touch to ask if dark matter might have similar structures to normal matter, and even if there could be such a thing as dark life forms. I put this to Andrew Pontzen.
Well, firstly, normal matter in the universe is really clumped together. It's not evenly spread out through the universe. It's clumped, for instance, into galaxies. Galaxies are collections of around 100 billion stars, and they're relatively compact, and there's a lot of relatively empty space between each different galaxy. Now, dark matter certainly does clump together in that sense. We know that for sure from observations of galaxies. This was, in fact, the original evidence for dark matter, looking at the way that material like stars and gases moving around in galaxies and inferring from that the strength of the gravitational field in galaxies, and from that inferring how much stuff there was there. And that's how we knew that there had to be dark matter. And in fact, because there's so much more dark matter than normal matter in the universe, there's around 5 times more dark matter than normal directly visible matter, its clumping is incredibly important in terms of determining the kind of structures that form in the visible universe, and the existence of galaxies effectively owes itself to dark matter. So in that sense, there are structures in the dark matter that are similar to the ones you see directly in the normal matter. Now, on another level, though, we don't really know what dark matter is. And so when we're talking about dark matter, we tend to be modelling it subject to some simple assumptions about what it's doing. And you get the best results for the evolution of the universe matching what we see in the real universe when you model the dark matter as completely non-interacting except through gravity. So other than the gravitational force which it exerts and which it's also subject to, it's not subject to any other forces. For instance, the electromagnetic force, which normal matter is subject to. And in fact, the really interesting structures in normal matter arise through things like the electromagnetic force. And all of chemistry, for instance, and therefore life, really arises through forces like the electromagnetic force. And for that reason, the evidence at the moment would suggest that you can't have really complicated structures that will be required to create what you might describe as dark life forms. So most likely there's nothing quite that interesting going on in the dark sector. But until we really know what it is, we can't say for absolute definite.
We've had a question from Dave Green that I'll put to you, Carolyn. He says, if the universe is expanding, but planets and stars are staying the same size, is the distance between Earth and the Sun increasing?
Well, this is going not so much from the effects of dark matter on our solar system, but looking at more the effects of dark energy. So staying on the dark side. I mean, space is expanding, and it's carrying the galaxies along with it for the ride. They're all receding from us, and we think they're being pushed apart by a force that we call dark energy. And this is currently accelerating the expansion of the universe. But the curious thing is that this dark energy, whatever it is a property of space. So the larger the distance between bodies, the stronger the push to drive them apart. Conversely, gravity, which we're a bit more used to, is a property of matter. And it's a pulling force, so that opposes the expansion. And gravity, the gravitational pull, is stronger the more mass that's there and how close you are to it. So whether the pull of gravity or the push of dark energy dominates over a given region of the universe depends on how much mass is there and how widely separated it is. If you're far apart, the push of the dark energy wins, but if they're close together, gravity's going to dominate. And you have to remember, in astronomical terms, our solar system is absolutely tiny. The planets and the sun and all the constituents of our solar system are very close together, and there's no question that gravity wins in that circumstance. And even on the scales of the galaxy, gravity is the dominating force. Even between groups or clusters of galaxies, gravity's gluing them together. And you're only going to get this expansion of space on the very largest scales, where you have sufficient space that the dark energy can dominate.
And finally, a question from Ben Lucky, which seems appropriate because it's the 50th year of the laser, and on the Naked Scientist show recently we were looking at laser technology. But he wants to know if you could use a laser to propel a spacecraft.
Well, yes, in theory you could. The way that any rocket works is that it ejects material backwards. And there's a principle of physics, the conservation of momentum, which says that if the rocket exerts a backward force on that material to accelerate it backwards, there must be an equal and opposite push, pushing your rocket forwards and accelerating it to move faster. And what matters is how much momentum the ejected material has, and that affects how great the push is forwards on the rocket. So could you substitute the exhaust gases of a conventional rocket with a laser or light beam? Well, yes, you could, because light is made up of photons, which, although they have no mass, do carry a very small amount of momentum. So, for example, if you put your hand underneath a light, then the light is actually exerting a very tiny downwards force on your hand. You don't notice it because the force is so small, but it is there. So likewise, a light on the back of a rocket would push it forwards ever so slightly, But the problem is this force is so incredibly small. I did a quick calculation this morning of what power of light source you would need to replace the thrusters on the Cassini spacecraft in orbit about Saturn, which can produce a force of 440 newtons. And the answer is you would need a 130 gigawatt light source. So that's equivalent to the output of several hundred power stations all going into one light source. So this isn't a terribly practical way of propelling a rocket.
But of course, there are actually ways you can use the pressure of light, for instance, in solar sail technology. And I think there's just recently been an announcement that the solar sail of the Icarus spacecraft has been unfurled.
So this is a serious question because it's very inefficient to carry large volumes of rocket fuel around the solar system. And so people are continually looking for new ways of controlling a spacecraft. And solar sails are one promising idea. How they work is you have a reflector which the sun exerts an outward force on due to radiation pressure. Also, the solar wind exerts an outward force. And what the Japanese Space Agency are doing at the moment is trialling this experimental solar sail Icarus, which is 20 metres across. And they're going to try and glide it down in the solar system towards Venus using the solar radiation pressure to control their direction as they glide through the solar system. And it will be fascinating to see how it goes.
That was Dominic Ford, Carolyn Crawford and Andrew Ponson discussing your space science questions. If you've got something for the panel to tackle, then get in touch by email to astronomy@thenakedscientists.com, or you can use our usual address, chris@thenakedscientists.com.
Keeping you abreast of the world's best science, The Naked Scientists.
This is The Naked Scientists, with me, Diana O'Carroll.
And with me, Ben Valsler.
And now, to help me with a rundown of the archaeological news from the last few weeks, I'm joined by my own tame archaeologist, Duncan Howett-Marshall.
Well, the first news item is the repatriation and recent reburial of the head of an Australian Aboriginal warrior who was killed and beheaded by colonial settlers in 1833. Now, in line with common practice at the time, his head was transported to England, where it was put on display in a museum as an anthropological curiosity, and eventually buried in an unmarked plot in a cemetery in Liverpool. His head has now been finally laid to rest in a traditional ceremony in a memorial park near the site where it is believed the warrior was killed 177 years ago in Western Australia.
So, who was he?
We know bits and pieces from the Noongar of Western Australia. There are accounts from white settlers at the time. His name was Yagan, and he was a leader of the Noongar tribe at the time when British settlers were first moving into the area around modern-day Perth. Relations between the Noongar and the newly arrived British were initially very good, but sadly this harmony didn't last, and there were misunderstandings regarding land management practices, where white settlers were essentially fencing off land for farming. Now, Yagan and the Noongar led something of an uprising against this, and as a result were implicated in the killing of several settlers. Now, they were declared outlaws, and a reward was offered for their capture.
But what happened next?
Well, Yagan wasn't without sympathy from members of the settler community, but even so, on the 11th of July 1833, Yagan was killed by two teenage brothers, and his head was cut off to claim the reward. Now, the head was transported to England and eventually put on display in Liverpool Museum.
OK, that sounds more medieval than 19th century, but what's happened since then?
Well, the Noongar people have been campaigning for the return of Yagan's head since the early 1980s, entrusting tribal elder Ken Goulburn with the task of locating the head in England. Now, he used the help of University of London archaeologists Peter Ucko and Cressida Ford, and successfully located the head in 1993. But it took nearly 6 years for it to be repatriated to Western Australia due to political wrangling and reported divisions within the Noongar community itself. Now, it's taken another 12 years for his remains to be reburied. Now, the delayed reburial of the head, which took place on the 10th of July, the last full day Yagan was alive 177 years ago, was due to disputes over the actual location of the site where he was killed. Now, the site is now the Yagan Memorial Park, and the traditional ceremony was attended by around 300 people, including Noongars and state representatives.
That's quite a turnout, but do you think that this will prompt the repatriation and reburial of other remains of Aboriginal people which are in museum collections all over the world?
Yeah, that's absolutely right. This certainly isn't a new phenomenon. In fact, the repatriation of Aboriginal remains has been going on for quite some time now. I was attending the World Archaeological Congress in Dublin in 2008, where the issue of repatriation of human remains was very much on the agenda, and the overwhelming feeling among the archaeological community is to work side by side with the descendant communities to bring the remains of their ancestors back and rebury them according to their traditional beliefs. I think we'll see much more of this in the future.
Yeah, I'm sure that's true, but I'd be surprised if the process became any easier. But on a lighter note, this next archaeological discovery at Stafford Castle can tell us something of the early relationship we had with domestic pets in the 19th century.
So what have they found at Stafford Castle, Diana?
Well, archaeologist Dr. Richard Thomas from the University of Leicester discovered a rather unusual leg bone amongst the skeletal remains of cats and dogs in the castle grounds dating to the late 19th century. And the leg bone was identified as belonging to a tortoise, perhaps the earliest evidence of such an animal being kept as a family pet in Britain. And these finds have been reported in the journal Post-Medieval Archaeology.
But how do we know the tortoise was being kept as a family pet?
Well, that's a good question. The fact that it was discovered alongside the remains of cats and dogs is a good indicator that this tortoise was being kept as a pet by the caretaker family, and they were living at the castle at the time. So Dr. Thomas stated that whilst there is archaeological evidence in Britain for turtles and terrapins from the 17th century onwards, these were largely kept for food, and the discovery at Stafford Castle is the first evidence we have for a land tortoise. Now, the 19th century was also a turning point in the general attitude society had towards animals as domestic pets.
What do you mean?
Well, in medieval and early modern Britain, society was deeply religious and the morality of keeping animals as pets was highly suspect. So exotic creatures, particularly those from outside Europe, generated a great deal of curiosity and fascination, but to keep them as companions was socially unacceptable. So domesticated animals were kept for food: milk, cheese, butter, meat, wool, leather, and so on and so on. In the case of dogs, many were kept obviously for hunting and herding. However, things began to change in the 17th century with the dog-loving Stuart kings.
Oh yes, I love those 17th century portraits of members of the House of Stuart sitting alongside their fluffy-eared King Charles Cavalier spaniels.
Exactly right, and dogs especially were seen as wonderful companions to have around the house, or in their case the palace, and so certain animals were now seen in a different light. And the famous 19th century sculptor Joseph Gott created a number of very sentimental sculptures of animals, and in 1822 the British government passed the Richard Martins Act, which prevented cruelty to farm animals, and this paved the way for the foundation of the Society for Prevention of Cruelty to Animals in 1824, which was the first animal welfare charity to be established anywhere in the world, and it was granted its royal status in 1840 by Queen Victoria.
What an incredible achievement, and something that I think we should all be very, very proud of. I guess the founding of the RSPCA set into motion all kinds of wonderful movements around the world dedicated to animal welfare issues that continue on to this day. But what of our tortoise bone at Stafford Castle?
Well, tortoises were unusual, but it was this age-old fascination with the exotic that made them desirable as pets around this time. But sadly, their popularity in the 20th century meant that thousands of wild tortoises were transported from the Mediterranean and North Africa to the UK, but they suffered terrible conditions, only to end up as pets in households which couldn't look after them properly. It was only with European legislation in 1988 that made the trade in wild tortoises illegal.
So there is a happy ending.
Thanks, Duncan. A very happy ending indeed. And that's all we have time for on this week's Naked Scientists. Next week, Helen Scales and Sarah Castor-Perry will be taking us beneath the waves for an ocean science-themed show. They'll be looking at how climate change is already affecting marine life at the poles, and what the future impacts of the Gulf of Mexico oil spill might be. If you'd like to find more astronomy news, questions and interviews, just visit thenakedscientists.com/astronomy.
And of course there's more archaeology, and that's at thenakedscientists.com/archaeology.
The Naked Scientists was produced by Chris Smith and presented by Ben Valsler and Diana O'Carroll. It was produced in association with the Open University. To discover a whole range of science content, including lots of interactive features, log on to thenakedscientists.com and follow the links to the Open University.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.